All right, continuing with section 2.4, rectangular components and unit vectors. So it's often good to resolve forces into two perpendicular components along the x and y axes. So if I were to, say, draw an axis, then like this maybe, so that I had the x value here and the y value here, then I were to draw a vector and start from the origin and head in any direction, doesn't really matter. Let's call it vector F just so we have it labeled. Well, I can project down and get an x component in the x direction to this vector. So this is f sub x vector. I can get a y component that heads up, which is fy. So I can then say that essentially our force F equals the vector summation of fx plus fy. So now let's define a unit vector. A unit vector has magnitude 1, and let's define the unit vector in the direction of x, and we'll call it I. It's a vector. And then let's define one in the direction of y. We'll also call that I. And they have a magnitude of 1. That's why they're called unit vectors. So, like so. And again, each of these has a magnitude of 1. So now I can then set up, and another way of looking at this actually is I equals 1 in this direction, j equals 1 in this direction. That's how we're going to define it. I guess we'll say this is positive, this is positive. So I can then rewrite my components here as the magnitude. So fx, the vector, really is fx, the magnitude of the vector, times the unit vector, and fy, same deal, equals fyj. Sometimes I put a caret, sometimes I put the strange hat like this. But they both mean the same thing. They're vectors. So then, f, the vector, equals the component in the x direction times I plus the component in the y direction times j. And I guess that's important enough to put a box around. So if I draw a triangle with these components so I can do some trigonometry, we know that this has a length of f, or magnitude of f. The magnitude of f equals, we'll just say f. And this is the magnitude of the x component and the magnitude of the y component. Then there's an angle between this and here we call theta. Well, then we can continue our definitions here. Then f sub x really is adjacent over hypotenuse. So f sub x over f equals cosine of theta, or we could write this like do some algebra. F cosine of theta and Fy equals F opposite over J, F sine of theta. So this we're going to define positive in this direction. This we're going to define positive in this direction, up and to the right. So finally, we could write the vector F equals the magnitude of F times the cosine of theta times I plus the magnitude of F times the sine of theta times I. Okay, now suppose I draw a rectangular coordinate system and I have a vector. Let's say this is my first vector. I'm going to draw a number of them, so I'm going to call this F1. So F1 is made up of components F1x I plus F1y j. So just a reminder, that would be this is F1, the length of F1x, and this would be the length of F1y. So these are the magnitudes of the components. Now I might have multiple vectors, so let's change colors. Let's do an orange vector over here, like so. Let's call this F2. So F2 equals, now we're going to keep track of the plus signs, even though we're doing general here. We don't really have to, because it could be taken up in the coefficient. But we're gonna keep things that are in this direction positive, and this direction negative, and this direction positive, and down this direction is negative. So this F2 is going to have a negative component, F2x I plus F2y j, because the j component is positive direction and the I component is in the negative direction. And then we can go with F3 even, a third one. Let's just go with the third one. Let's take it along an axis. Let's go down, right down the y-axis, just so you can see that things can go down axes. And in this case, we're not going to have an x component, but we will have a minus F3y j component. So, what is the resultant for these three forces? Well, I could stack them all together and try to come up with something. But the easiest way to do this is just to sum the components. If we sum the components, we're going to get the correct answer. So F1 plus F2 plus F3 equals our resultant. So this then, all I need to do is add the components to find the components of this resultant. So this is F1x minus F2x I. There is 0 here. And then plus F1y plus F2y minus F3y j. And that's all you have to do. And that'll give us both the magnitude, or that'll give us a vector, and it'll give us the vector in the correct direction. So in essence, what this results in is R1 or Rx. We don't need an R1. Rx I'll put parentheses here, I plus R, Y, J. So that's the scalar component in the X and Y direction. So this term resulted from summing the forces in the X direction, and this resulted from summing the forces in the Y direction. So we have the magnitude, or we have the vector. So what is the magnitude? So R, what does R equal? The final magnitude. Well, R equals this Rx squared plus Ry squared. We take the square root of that. So then if this is R, and this of course was Rx, and this is the length Ry, well, this is also the length Ry, which means we have a theta, and we can find the direction of R with respect to the x-axis as Ry opposite over adjacent equals the tangent of theta. So the arctangent of Rx or Ry over Rx equals theta.